Project is this hand chopper. It's basically a fun and exciting way to chop up your fruits and vegetables that you're totally gonna eat later. It works by putting some food into the glass jar and then attaching this fancy lid on top, then slapping the white plastic piece on top that we've named the pommel, which compresses a spring that allows the blades to descend and chop up the food. This full assembly comes with 9 parts: the glass jar, the white plastic pommel, the brown plastic lid, the white plastic cap attached to the bottom of the lid, a rod, 2 blades, a spring, and a washer. If you unscrew the jar, you're left with the lid assembly. When you take all the plastic parts off the lid, basically the cap, the brown lid, and the white pommel, you're left with a bunch of metal we've named the blade assembly. So the rod, the spring, the washer, and the 2 blades welded on one end.
The glass jar was manufactured using the blow-and-blow method. The plastic pieces, including the cap, pommel, and top, were all injection molded. The washer and spring were standardized parts that can be bought from a different company. Changes we made to our product were the size and shape of the blades and the material and geometry of the container and top. These changes were made because the blades in our original design were not sufficient for cutting large items. The blades are now larger and have a zigzag geometry that does a better job of cutting the food into finer chunks. The container was changed into an extruded plastic cylinder, and the top was redesigned for a simpler injection mold. These pieces were then plastically welded together, which gives ease of manufacturing and ease of assembly.
So for our DFA analysis, we are seeking to maximize its theoretical and practical efficiencies and minimize the complexity of assembly or manufacturing. So we set a target of 80% for both practical and theoretical efficiencies because we want it to be function most of the time. Meanwhile, lower target values are set for error proofing, handling, insertion, and secondary operation, which are 0.5, 1, 1.5 and 0.7 respectively. From our initial design analysis, we have found that both washer and cap are not needed for the product to properly function. As a result, both components are removed from our final design. We also decided to combine the top and the container together so that the top can replace the role of the cap, which is essentially a barrier to compress the spring. The removal of both washer and cap and the redesign of the container have resulted in 100% theoretical and practical efficiencies in our final DFA analysis. This is because each of the parts of the product is now essential in contributing to the product's functionality. We also noticed that the values of error proofing, handling, insertion, and secondary operation are also lower than the initial product. This shows that there are improvements in our final design and can contribute to maximizing the efficiencies of the product assembly and manufacturing. Overall, the DFA analysis for our final design has met our expectation.
The new manufacturing processes for our updated design were the extrusion of the cylinder, the plastic welding of the top to the cylinder, and the bulk deformation of the blades through bending.
We didn't see it coming. It was 1 minute it was fine, clear day. Oh, my boys were out in the fields, and little Sally tried to go get help. Then the next second, well, we'd never seen anything like it. Nobody knew what to do. We didn't know how to react. It all just happened so fast, and 1 minute it was there, next it was gone, and well, poor Tommy.